Hey everybody, welcome to the Cast AI Distributed SQL Summit 2021 presentation. Today I'm super excited. We're going to be presenting an approach to scale a Yugabyte database cluster leveraging AWS Spot instances. These are preemptible instances at a much lower cost than you would be normally spending for scaling a cluster such as this using on-demand instances. So let's get started. So what are we going to cover today? We're going to cover an overall setup review. We're going to start with a basic vanilla EKS cluster on AWS. We're going to connect that cluster to Cast AI for automated provisioning of infrastructure as well as scaling. We're going to then review the Yugabyte deployment, deploy the stateful set, Yugabyte stateful set on this demo cluster, and we're going to show how the instances get provisioned. Then we're going to set up a benchmark and some gotchas and some setup details that I think are super important. Finally, we're going to talk about just some basic tooling required to collect metrics such as Prometheus and Grafana. We're going to use those to kind of gather some results, run and tune the benchmarks, and then I'm going to do a live demo of a Spot instance interruption or preemption. We're going to watch actually how the cluster reacts. I'm going to review our results and then kind of conclude with some final thoughts. So what is the use case? We're starting with a very basic cluster of 3 nodes. These are C5A8X large nodes. They're 32 CPUs, 64 gig of RAM, and $1.23 per hour. So the monthly cost is just multiplied by the number of hours in the month. We're using elastic block storage to for our persistent storage layer. And you'll notice that there are masters and tablet servers distributed evenly across all of these instances. So this ends up being a cluster that costs $3.69 an hour or $2,656 per month roughly. And that's great. But what if you got to a position where all of a sudden you had a burst in your business, maybe it's holiday season, or you have another factor that's causing you to have to double your throughput. So normally that would be doubling of your costs. You would just simply have to buy or rent an additional 3 on-demand instances. But here I want to walk you through an approach where we actually use 3 additional Spot instances, and we might actually get different instances provisioned in the Cast model when we go to do the work. But essentially, we're going to provision an extra 3 nodes for double the capacity, so 100% more read-write capacity throughput, but we're going to effectively average down the cost of a node by 38% because we're going to be taking a blended rate of $1.23 per hour and 30 cents per hour. And you can see how at large scale, this can be a massive cost savings. And then of course, we have our load generator pod on the left side of this diagram, which I'll talk about. This all works great with the one caveat that you have to be able to handle Spot terminations gracefully and automatically. So for those of you who don't know, a Spot termination, basically, you're getting a highly discounted instance from AWS with the caveat that when they have a customer that's willing to pay full price for that instance, they are giving you 2 minutes notice to remove your application and shut down before they actually forcefully terminate the instance. So this is how do we make it work in all of this chaos? This savings all looks great, but we really have to be able to handle this one edge case, which happens all of the time in order for this whole approach to work. So we're going to walk through that, and at the end of this demo, we're going to actually show a forced interruption that we're going to simulate. So just on the cost side here, our double size cluster, is going to be $3,300 a month, and that is $4.59 per hour relative to the $3.69 per hour for just the 3-node cluster. Okay, awesome. So let's get started. Some basic things that you need to know. You have to install the AWS command line tool. There's a command line tool called EKSCTL, which helps you create EKS or Kubernetes clusters on Amazon. We're going to be using the Lens IDE. If you haven't used it, I highly recommend it. It's a great tool. And then you are also going to need to have Helm installed for various components that we're going to install, like Prometheus. Finally, configure AWS so that you can actually access your command line with your secret and your with your key and secret. And now the command at the bottom of this screen is the command that we're going to run to create the cluster. And we're calling this YB spot demo in US East Region 2, which is in Ohio. So I created this cluster actually with a single node. And the reason I created it with a single node is I really didn't need, we didn't need all that extra spare capacity. So this process takes about 20 to 25 minutes when you're doing it on your own. This tool uses CloudFormation, and so it does a whole bunch of terraforming in the background. But at the end of the day, you're going to have a ready cluster with your kube config file updated and ready to access the cluster from command line or from our Lens IDE, which I'll show you in a moment. So now that we have our cluster, we need to connect it to CAST. So this is the process. I'm going to just show you really quickly. It's a super simple process. So when you register for CAST and you're kind of in the clusters dashboard, you click on Add Cluster and Connect Cluster, and then you're going to get a command line utility here to just to run wherever you have access to that Kubernetes control plane. And that's going to install a read-only agent. That read-only agent will then generate a savings report and set you up for the next phase, which is the full automation and onboarding of the cluster. So I've got two clusters that are kind of onboarded here. We're going to use this one here, and you can see that it'll generate a savings report like this, which will tell you what the current cost is, where you are in the optimal or optimization process, and then some additional details on this report. So let's go back to so now that we've got our cluster connected on CAST, what we want to do is enable it for scaling. So I'm actually going to walk you through some of the policies that we're going to set up. So it's a very intuitive set of policies, but let's go take a look. So once you've got this enabled and you've got the kind of automation credentials created, and there's a script to do that as well, you're going to have access to this kind of policies page. And so the policies page is, I'm going to really just cover the ones that we really care about. There's really two policies that we care about. We care about the unscheduled pod policy. So when we go ahead and deploy the Yugabyte YAML file, and I'm going to provide that to you in our examples GitHub repository, these pods are going to be created without any room. So we need to have the unscheduled pod policy to create the infrastructure required for us in order to fulfill the needs of the deployment. And so we're going to turn that policy on. And the only change that I've really made in the settings is I've given very little headroom. So we don't need a whole bunch of extra space. We just want what the deployment file is asking for. And then the other really important policy that we want to turn on is this spot or preemptive instance policy. This allows, with some special annotations, with some special node selectors and tolerations in our YAML, to let CAST know that we intend to deploy some of these on spot instances. One of the really important features that we're going to use here is this kind of feature that allows you to balance preemption or interruption with cost effectiveness. So by default, this is set to the most cost efficient setting. But if your workload was sensitive and you didn't want to endure as many interruptions, but you were okay with taking a smaller discount, you could set this to a balanced approach or a least interrupted approach. You're going to sacrifice 10 or 15% on the discount of the instances, but you're going to have way fewer interruptions. Cool. I'm going to leave the setting as it is here. And let's go to the next step I want to get to, which is really reviewing the deployment file. So I've got that open in Visual Studio Code here. Now, I'm not going to go through the whole deployment, but there's a couple of things that are really important. So I'm going to search for the keyword replica. And you'll see the first spec we have is for our masters. Yes, we want to have 3 replicas. And this is really, there's really nothing kind of special here, other than we probably have some anti-affinity rules to make sure that those masters, or we're even okay with allowing the masters to end up on the same nodes because they're not on highly volatile nodes. But the next step here we have is the tablet servers, the T servers, and here is where we get into a bit of an interesting configuration. So you'll notice that here I've got a replica count of 3, and this is really pretty much a normal deployment. The only thing that you'll probably see that's of interest here is that in our resource requests, if I can just find it here, we will see we'll see 14 CPU requests. We'll see it in the next deployment in just a second. But so that's one stateful set. The second stateful set is the one that we call, let's find it here, is the one that we are calling YugabyteDB server spot. And this is the extension of the cluster, if you will. This is adding 3 additional pods to our stateful set that are going to be running on spot instances. So again, we have a replica count of 3. And then we have this is the kind of the piece that's pretty interesting. So the first piece is this toleration that you see exists on line 493. What this toleration does is it tells Cast AI that if there's an opportunity to run on a spot instance, I will tolerate running there. It doesn't force the pod onto a spot instance, but it says, hey, I'm okay to run here. The second piece, which is this node selector, enforces the rule. So it says, no, it's not only that I'm okay to run on spot instance, but I must run on spot instances. So if this node doesn't have a scheduling label on it for spot instances, I'm not going to run. So these two in combination really force these pods onto spot instances. And then one other interesting piece we have is the affinity rule here. This is a pod anti-affinity rule. And basically what it's saying is, look, we don't want any of these T servers running together. So whether they're on spot or on demand, we want them fully distributed across their own individual nodes, not to have resource contention. And then I think if we take a look at the resources here, if we take a look at CPU here, we'll see that we requested 14,000 millicores, which is the same as 14 CPUs, and 226 gig of RAM. Awesome. So that's pretty much all I want to show you on the deployment. We can go ahead and take a look at, there's a couple of other pieces that we want to take a look at. I'll show you how the deployment actually manifested in the cluster itself. But just as a reminder, you probably want to have metric server installed. I have a link here in the slides. You want to have the Kubernetes Prometheus stack installed, and that's why you need Helm. And then this is all of the examples that we're showing are in this GitHub/Cast AI examples directory. This will all be under the Distributed SQL Summit example folder. So let's take a look at the cluster now that we've got Yugabyte fully deployed. Let's take a look at what we've got. So if we actually look at the stateful sets here, and I switch to the Yugabyte area, you'll see that I've got my masters. I've got the T server, which is on demand, and I've got the T server, which is on spot, and they are 3 individual pods. So this is the exact configuration that we asked for in the YAML file, and it's distributed across these specific nodes. You'll see that actually the better view here is in the CAS console. When we look at the kind of the savings, available savings report, you'll see down here, there are these 3 C5A extra larges, right? Remember, we talked about $1.23 per hour. And then we have these interesting spot instances. So we have one spot instance, which is a C5 4X large. We have another one, which is an MD5 8X large. And then we have one, which is M5ZN 6X large. Now, the first thing you'll notice is that there's a whole mix of instance types. There's no concept of node pools here because we're not scaling on individual instance groups or pools. We're actually saying whatever capacity we need to satisfy the deployment is what we're going to bring into the cluster. And so I did this scale up just prior to this demo. But if you want to take a look, if you want to look up what an M5ZN is in AWS, I think you'll be surprised. Many people probably don't even know that instance type exists. And that's the whole dynamic of kind of the freakonomics of CAST. Because we're looking for the lowest cost instances at any moment in time, we'll often find highly overlooked instance types where people think, oh, that's too much horsepower, we don't need that, it's going to be too expensive. But in reality, when you look at the spot pricing, it's much cheaper than going for a regular vanilla instance. So that's awesome. And then if we look at the kind of the scaling log, from when we did the demo, you'd kind of see this. It's actually, I recorded it in from the audit log. You'd kind of see that scale up happen here. So this is where we added those C5 8x larges, and then this combination of funky instances that we created. Let's take a look at how Yugabyte sees these instances. So if we open the Yugabyte console for the user interface, this is for the tablet servers, and take a look at the zone, because we've used the zone kind of to represent on demand and spot. So I've got three zones that are three instances that are on demand and three instances that are on spot, and that's the tablet peer availability zone breakdown below and in the lower table. And it looks like they're all alive, they're all humming and ready to kind of serve transactions. So that's great. We've got everything set up. We're ready to start the actual benchmarking. So to start the benchmarking, probably a lot of people have used the TPCC benchmark tool. I want to use these numbers to kind of compare on-demand only versus spot price, spot instance clusters, kind of larger clusters, smaller clusters, and we'll show you some results at the end. But the basic premise here is we have a pod, which is a client pod, and we put that on a separate server, not to interfere with the actual workload. So we've got that on a separate spot instance, and you can exec into that pod. You have to install the basics like Java and other utilities, download this benchmarking tool, which I've already done. And there's really two steps that you need to perform. You need to create the schema, right? So this is the first step here to create the schema. And then you need to load the warehouse data. So really important, the smaller the number of warehouses, the smaller your cluster is going to be in terms of throughput. So, for such a large cluster that we've created here for 6 nodes, we really need 300 warehouses to push the limits of the workload here. So this is the most kind of sane set of settings for me, 300 warehouses, 10 loader threads. And I highly recommend you split the loading process from the benchmark execution process, because the loading process can sometimes be a little less stable and you might need to retry it a few times. So you don't want to mix the two together. Just one note on the node endpoints. For step 1 and 2, there is no need to provide a whole list of endpoints for the cluster. You only need to create the schema on one tablet server, and you only really need to load the data on one tablet server. Yugabyte will do a great job of writing to all of its peers without you having to specify all of the data. Here's how you get the endpoints. So what is the IP address of my nodes? Well, you do that in Lens. What you can do is you can go to endpoints here, and in our Yugabyte namespace, you'll see there's a master's endpoint and a T-server endpoint. And on the T-server endpoint, just cut and paste this. This is the list of IP addresses. So there's 6 of them, 3 on demand and 3 spot, that are going to be associated with this entire cluster. And again, when you're creating the schema, just pick the first one. It doesn't really matter. Same when you're loading the data. Awesome. So loading the data takes a couple of hours, right? So that's just a fair warning. And one thing that I noticed is it's pretty CPU and time intensive. So this is kind of a screenshot of that whole load process. The left image here just shows the top of the pods. You can see that they're all pretty busy in a nicely distributed fashion. And you can see kind of the screenshot that I took. At one point, we were using 30 CPUs out of this cluster just to load the data. I would say loading the data is even more CPU intensive than running the benchmarks themselves. Once you've loaded the data, basically you're ready to go. You can execute the script to actually run the TCP benchmark, and you're going to get a result that kind of looks something like this at the end of it. So create schema, load, and execute. And this is kind of the sample output of an execute, which will be available in the samples that we provide. And you can see here, the key 3 statistics that I'm looking for is the transactions per minute. So in this case, we got 3,657 transactions per minute. We had an efficiency score, and then we had a throughput requests per second score, right? So, and what we want to do is we want to compare this to an on-demand only cluster and a on-demand plus spot cluster, and we'll see those in the results. But let's return back to the first problem. Let's assume everything works great. We're getting fantastic benchmark results. We're really happy with our cluster throughput. But what happens in this situation where we have a spot interrupt and we lose a server. So let's take a look at our cluster configuration right now. Let's go back to our nodes. And what we're going to do is we're going to pick a node that we're going to victimize. So we know that these ones with taints have a tablet server on them. So let's pick one here. Let's pick, so I see this one is running YugabyteDB server spot 1. So that's perfect. I'm going to copy that instance name because we're going to actually go into Amazon and forcefully terminate it, right? And so from a cast perspective, we expect cast to really pick up that termination. We'll see it in the audit log and replace that instance as soon as it's terminating. So I'm just going to pause for a second while I log on to AWS. We'll be back in just a second. Okay, so I'm in the AWS console now under compute. Let's find that instance that we care about here. So let's filter here. Great, we've got this node, and we know that it's running the T server number 2 under spot instances. So what we're going to do is we're going to actually, we can't stop the instance. We're going to terminate the instance. This is really a kill of the instance. And it's going to delete EBS volumes, which is totally fine. This isn't the EBS volume where the data is. This is kind of the root volume. So I'm going to go ahead and terminate. And that's going to start this shutdown process. Notice this was that funky M5ZN6X large instance that we're terminating. So we should see a couple of things. First of all, let's go to our Kubernetes cluster, right? And let's take a look at what the node list says. And what we should see is one of these nodes will start to taint very quickly. So we're going to get a signal as soon as this is terminating. And then we're going to see, here we go. So you see how this node stopped being ready, and we actually lost it. And the reason we lost it is because cast removed that node and is starting provisioning the new instance right away. So I want to see the Yugabyte view before it's too late. Let's take a look at the tablet server view. 62 seconds, we have a dead tablet server, right? So we need to see if this situation will resolve itself over the next minute or two. Let's switch over to the cast console and take a look at the audit log. And so what do we see? We see that a node was added through unscheduled pod policy. In this case, it was an M5DX 8X large, different instance type, but this is what we found in savings. So now we have this particular node that's being added to the environment for that T server to be deployed on. And if we look at Lens right now, we'll probably see that we're going to get another node in this environment in just a minute or two. All right, guys, I probably didn't need to pause. So you guys see that this spot 2, it's being initialized right now really quickly. And the warning is here is there wasn't enough capacity in the cluster. Remember, because we had a computer taken away from us. This is why we had a cycle where cast created the extra spot instance node with the capacity for this cluster. And as soon as, and this is about 2 minutes old, as soon as this pod initializes, we should have a flip state from dead to properly running. So let's take a look. I don't know if the Yugabyte user interface is updated yet. It probably needs another. Oh no, there it is. So right away we got a replacement on spot. The whole thing took 2 minutes. The whole cluster was up and running in the meantime, being load balanced by the other T servers. And now we have a scenario where we have a running environment. So this was the scenario where the spot interrupted and we went through that live. So what are the results of the benchmark? So we've got, I've got a couple of different scenarios. The first one was an on-demand 3-node cluster. And with 300 warehouses, I couldn't get the benchmark to run properly because there were just some data consistency issues with the size of the warehouse count that we loaded. However, when I scaled that back to run against 100 warehouses, it worked pretty well on 3 nodes. And then we got a transaction per minute count of 1,208. So I want to show you guys this calculation on cost. So we had a 93% efficiency, 45 requests per second. The average node cost here was $1.23. Remember, we saw that based on our first diagram. So it ends up being 5 cents per 1,000 transactions if we do the math. So if we did the algebra. How does that look like for 6 nodes? So for 6 nodes, we were actually able to get to 300 warehouses without a problem. These are all on demand. We got the 3,628 transactions per minute, which is great, 94% efficiency. And because we were able to get more throughput because of the higher warehouse count, we brought our average transaction for 1,000 transactions per minute down to 3.3 cents, which is great. But can we do any better with 6 nodes? Remember, this is the scenario that we actually were demoing just now. So it turns out with 6 nodes, we got roughly the same throughput, just a little within a statistical margin of error that is negligible. We got the same kind of efficiency rate, 136 roughly requests per second. But take a look at the average cost per node. That went down to 71 cents, almost 72 cents. That makes our effective cost per 1,000 transactions 1.9 cents. One little interesting test that we did, I dropped the node count from 6 to 5, so 1 less node. And I was expecting to see a lower throughput, lower transaction rate. But in fact, we got almost the same TPMC count, so transaction per minute count, similar efficiency. We were able to get the average cost per node to 67 cents, and that got us to a transaction per 1,000 cost of 1.5 cents. So pretty cool. I have to investigate a little bit deeper why that drop in node count really didn't make a difference. It's probably to do with the replica factor. So we still have a replica factor of 3. And we still have 3 nodes working to read and write at any one time. But that's just a hypothesis of mine. So at the bottom are just some graphs representing that same data. So let's wrap it up with some final thoughts. So smaller clusters have a hard time loading and processing benchmark at scale. You really need to have that cluster scale for the workload that we were targeting. Spot instances provide a significant per transaction savings over on demand if, and here's the big caveat, if spot instance interruptions can be handled automatically and seamlessly. And that's what I hope you saw from the demo today, how we were able to kind of seamlessly make that happen. Finally, varying instance types does help with interruption stability. Remember, because if AWS is all sold out of C5As, and that's the instance type you've hard coded, not being able to select the next one in the market is going to greatly affect your stability. Also, selecting instance type with the least possible chance of interruption gives you great advantage in cluster stability. So if you remember, this is kind of that policy page that I showed you that allows you to kind of configure this balanced versus cost efficient versus least interrupted approach. And with a replication factor of 3, there wasn't a huge difference in throughput between 6 nodes and 5 nodes. Both mixed and on-demand instances really didn't make a difference. We got the same performance from the least expensive instances as the most expensive, which were on demand. And then some things left to try. I mean, we did install Prometheus here. So we have Prometheus kind of set up here, monitoring the cluster utilization. That was really important for us to figure out if we have good utilization of the resources that we allocated. But we really want to bring in the Yugabyte metrics, which are available from Yugabyte, and a nice Grafana dashboard. So those are things we're going to try and probably post them as demos as well. And then also a different set of combination of warehouses and connection counts to find the breaking point. So I think that's those are kind of the conclusions from this set of experiments. We're really excited about the cost effectiveness and the throughput we were able to achieve in this kind of scaled scenario that looks like this. Really want to thank you guys for your time and attention on this. I think cost is going to be a huge deal in the years to come as everything moves to the cloud. So we're really excited to be able to provide some of these insights and solutions. Thanks everyone, and hope to see you everyone in person next year.